Hello, welcome. Today we will discuss about quantum mechanics. That is the development and origin of quantum mechanics. Quantum mechanics actually is a branch of physics that deals with the behavior of particle in microscopic level. Or simple words we can say it's a science of small things. First we will discuss about the crisis in physics that demand quantum mechanics. Or what is the necessity of quantum mechanics or the emergence of quantum mechanics. The success story of classical physics is maintained till the end of 19th century. That is mechanics and gravitation, which means Galileo, or which is contributed by the so-called theories from Galileo, Newton, Kepler, Euler, Lagrange, Hamilton, etc. There are a lot of theories that can be explained the phenomena related to mechanics and gravitation. Then coming to the electromagnetism, Coulomb's law, Ampere's law, Faraday's law, Maxwell's equation, there are a lot of equations or theories can be explained the phenomena, or these theories could explain the phenomena related to electromagnetism. These theories could explain the phenomena related to electromagnetism. Then coming to thermodynamics, Clausius, Kelvin, Maxwell, Gibbs, there are a lot of theories which can explain the phenomena related to thermodynamics. And even in optics, Fermat's principle, Huygens theory, Young's theory, Bragg's law. So there are a lot of theories, or those theories can explain the phenomena related to optics. So it was thought that all basic phenomena could be explained with this classical theory at that time. But there are few phenomena which could not be explained with the so-called classical theories. So here we will discuss the examples of breakdown of classical physics, or the breakdown of classical physics. The first one is the stability of atom. See, as per the Rutherford atomic model, the positive charge is concentrated at the center and electrons are revolving around the nucleus. So the center is the nucleus and the electrons are revolving around the nucleus. See, electrons is a charged particle. As per our convention, it is negatively charged particle. As we know, see, the electrons are revolving around the nucleus, that is in a circular path, which means that it is there is an acceleration, even though its magnitude is same, direction is always changing. So this charge is accelerating. As per the electrodynamics, accelerating charges emit electromagnetic radiation. Electromagnetic radiation is nothing other than energy, which means that electron loses its energy. That leads to electrons may fall into the nucleus as per the classical theory, which is not observed in normal case. That is, if electron is orbiting, which means that it is accelerating. As per the electromagnetic theory, accelerating charges always emit electromagnetic radiation. That is the fundamental theory behind the working of antenna. Anyway, accelerating charges emit the electromagnetic radiations, so it may fall into the nucleus. So there is a question: why don't atoms disintegrate in nanoseconds? So this is not observed as per this is not observed, but it actually may happen as per the classical theory, but it is not observed. So there is a crisis. And at the same time, as per the classical theory, the path of the electron should be a spiral one, which means that there should be a continuous spectra instead of discrete line. That we will discuss, that we will consider as a second crisis in physics. So classical physics could not explain the hydrogen spectra, which means that hydrogen spectra consists of discrete set of lines instead of continuous lines. As I told you, the path of the electron is a continuous path, just like a spiral path. If that is the path, then there should be the spectra should be a continuous one. But instead of that continuous spectra, we will get a discrete spectra, which cannot be explained with the so-called classical theory. And another one is the classical theory failed in explaining the optical spectra, that is, any substance when raised to a higher temperature emits spectral lines. which could not be explained with the so-called classical theory. So the first one is the stability of atom, second one is fine structure of spectral lines, third one is any substance when raised to higher temperature emits spectral lines which could not be explained with the so-called classical theory. Then fourth one is photoelectric effect could not be explained with the classical theory. Then black body radiation. Okay, then wave property of electron. So at the end of 19th century, there are a lot of physical phenomena which could not be explained with the classical theory. So we will discuss one by one what is black body radiation. Actually, black body radiation or explanation of the black body radiation is the birth of quantum mechanics. So we will discuss what is black body radiation. Before discussing what is black body radiation, we should know what is a black body itself. With simple words, we can say black body is a theoretical object that absorbs 100% of radiation that hit on it. Therefore, it reflects no radiation. It appears perfectly black. Okay, so black body is an object which absorbs all the radiation that falls on it. It cannot reflect anything, but it can radiate. Once again, I would like to tell you, black body is an object which absorbs all the radiation that falls on it. It cannot reflect. It cannot reflect, but it can radiate. So it appears to be a perfectly black body. So this is a symbolic representation of a black body. See, there's a cavity, there's a small hole. You can find a yellow light falling on this cavity. So what happens is there is a total internal reflection, which means that the light is confined within the cavity. Okay, this is not the black body, it's a representation of black body. See, in this figure you can find that light is coming, and after hitting the walls of the cavity, see, there's a total internal reflection, which means that the light is confined within this cavity. Okay, it is not reflected. Okay, so we can view a black body as a small hole cut into the cavity is most popular realistic example. This is a realistic example. None of the incident radiation escapes. See, from this we can find that no radiations escaped from this cavity. So black body is an object which absorbs all the radiation. It cannot reflect. Okay, then there is a question: what happens to this radiation? See, the radiation is absorbed by this black body. Then what happens to the radiation? There is a question. Okay, so we will discuss what happens to this radiation. Radiation is absorbed in the walls of the cavity. This causes heating in the cavity walls. See, the black body which absorbs the radiation, after absorption what happens is this radiation causes heating of the cavity walls, which means that black body get heated, or the temperature of the black body may rise. Okay, so how it happens is that atoms in the walls of the cavity will vibrate at frequencies characteristics of the temperature of the walls. Depending upon the temperature of the black body, the atoms may vibrate. So atoms may vibrate at a frequency. That frequency is a function of the temperature of the wall. That we will discuss later. Okay, so what happens is the black body absorbs the radiation. That causes a heating effect. How it happens is that atoms of the cavity that may vibrate, that vibrational frequency depends upon the temperature of the black body. Okay, so these atoms then re-radiate the energy at this new characteristic frequency. Okay, so now I think it is clear. So the radiations absorb the black body. After absorption, what happens? The atoms of the cavity or black body that may vibrate at its characteristic frequency. So these atoms may re-radiate, not reflect. It may re-radiate the energy at this new characteristic frequency, not the frequency of the incident light, maybe the new frequency. Okay, so the emitted thermal radiation, so the emitted radiation can be viewed as a thermal radiation. So this emitted thermal radiation characterizes the equilibrium temperature of the black body. Now we can see the black body absorbs all the radiation falls on it and emits radiations of all wavelengths when it is heated. See, black body absorbs the all the radiation that we already mentioned, and it emits radiations of all wavelengths. There is a possibility of radiation of all wavelengths. That wavelength depends upon the vibrational frequency of the atom. These radiations independent of the nature of the substance. See, this is important. The radiational frequency is independent of the nature of the substance, but it's a function of temperature of the black body. See, the black body which absorbs all the radiations, and after absorption there's a possibility of radiation. That radiation frequency is not a function of the material of the black body, but it is a function of the temperature of the black body. Okay, so radiation from the black body is a or radiation from the black body is depends only on the temperature, not on the material. So therefore black body can be said to be a perfect absorber and a perfect emitter, not a reflector. Okay, so black body theoretically it's a perfect absorber and a perfect emitter. The energy density has maximum value at a particular frequency. Then we can find the spectral distribution of black body. So before discussing the spectral distribution of black body, see, this is what actually experimentally observed, which means that suppose there is a black body, and through using a spectrometer we analyze the radiations coming from the black body. Suppose our black body is at a particular temperature called, suppose it's a 5000 Kelvin. See this graph, 5000 Kelvin. Suppose our black body is at a 5000 Kelvin. Okay, then using a spectrometer, yes, using a good quality spectrometer, some sort of spectrometer, we analyze the radiations coming from the black body. As I told you, radiations coming from the black body consists of all the wavelengths. For example, black body can emit blue light or green light or yellow, orange or red, whatever it is, or before in infrared or ultraviolet radiations. Okay, so see, radiations coming from the black body is analyzed using a spectrometer. Okay, so this spectrometer can detect all the wavelengths. Okay, so radiations from the black body is analyzed using spectrometer and it is recorded. Then you can find that all wavelengths, radiations of all wavelengths are detected. For example, see in this graph, y-axis is intensity and x-axis is wavelength. Okay, for example, see, this is just an example. Consider the 5000 Kelvin temperature. Okay, for a particular temperature 5000 Kelvin, see wavelengths of this range. See, I hope you noted the cursor. Radiations of this wavelength, that is blue light, which is having intensity of this level, which is just greater than 3. Not 3, just greater than 2, in between 2 and 3. Okay, then for green it is much higher, intensity is much higher. Then yellow again much higher. Then orange again much higher. Then red again much higher. Then after that it decreases. Okay, so what is the difference between energy and intensity? Intensity means number of photons and energy related to the frequency. Okay, for example, I would like to tell you, see the green light, which is for example, it's suppose it is 10 photon, but yellow it is 20 photon. For example, an arbitrary value. For red it is 40 photon. So number of photon is higher for the particular wavelength. Okay, So that is the difference between intensity and frequency. Frequency is directly related to energy, and intensity is related to number of photons. Okay, so this is what actually happens, or observed in black body spectra. Okay, so black body is a perfect absorber and also a perfect emitter. So the radiations emitted from this black body is analyzed using this spectrometer. So then we draw a graph, which means that wavelength of this one having intensity this, wavelength of this one having intensity like up to this, wavelength of this one intensity this, wavelength of, so wavelength and intensity relation for a particular temperature. Okay, and another temperature for 3000 Kelvin, this is the graph, and 4000 Kelvin, this is the graph, 5000 Kelvin, this is the graph, and 6000 Kelvin, this is the graph. Okay, this graph is plotted by getting the data from this spectrometer. Then we have to analyze, or we have to analyze this black body spectra. Okay, what are the inferences that can be observed from this black body spectra? What are the inferences? See, look at this graph. The intensity, we can say intensity increases and decreases. For 4000 also increases and decreases, 5000 also increases and decreases, 6000 also increases and decreases, which means that we can say the intensity distribution is not uniform throughout the wavelength. Look at throughout the wavelength. Suppose the intensity is same for this wavelength, for example 2 or 3, whatever it is, the graphs just like a straight line parallel to the x-axis. If this intensity distribution is uniform, then the graph should be a straight line, but it is not a straight line. So we can say the first inference is the intensity is not uniformly distributed. Second one, I think from analyzing this graph you can find the we can find as the wavelength increases, the intensity increases to a maximum value and after that decreases. For a particular temperature, the intensity is maximum for a particular wavelength. We can say for a particular temperature, intensity is maximum for a particular wavelength. For example, for 3000, for this wavelength intensity is maximum. For 4000 we can find this wavelength intensity is maximum. For 5000 it is this wavelength this intensity is maximum. For 6000 this is the case. So the first inference is the intensity is not uniformly distributed. Second one is there is a lambda max. For a particular temperature, intensity is maximum for a particular wavelength. The third inference you can find, as the temperature increases, see what is the nature of this lambda max? The x-axis is wavelength. You can find as the temperature increases, this is lambda max, temperature increases, it goes to here. Again temperature increases, it goes to here. Again temperature increases, it goes to here, which means that initially this is the wavelength, this is the wavelength second case, this is the wavelength third case, wavelength corresponding to maximum intensity, and this is the wavelength corresponding to maximum intensity. So we can find as the temperature increases, the lambda max shifted to lower wavelength side. Is it clear? Okay, then the fourth one is, as the temperature increases, the intensity or energy radiated from the black body is also increases. As the temperature increases, intensity or energy radiated from the black body also increases. From this graph you can find. And the fifth one is, see the total energy radiated from this black body. This is the energy distribution. Then the total energy radiated from the black body can be calculated by integrating this graph, which means that the area under the curve, okay, the area under the curve. For example, this 5000 Kelvin, the area under this curve gives the total energy radiated from the black body. Okay, so these are the spectral distribution of black bodies. First one is energy is not uniformly distributed. At a given temperature, intensity of radiation increases with increasing the wavelength and becomes maximum at a particular wavelength, which is called lambda max. Okay, or increasing the wavelength further decreases the intensity of heat radiations. Okay, I already mentioned. The third one is as the temperature increases, the lambda max shifted to lower wavelength side. Okay, this is a graph. I think it is clear for you. I'm just repeating for the sake of people, those who are catching. The fourth one is as increasing temperature causes an increasing energy emission of the all wavelengths. It's very clear from this graph. Then the area under the curve represents the total energy radiated from the black body. Okay, this area increases with the increasing temperature. See, this is the area. This area increases with the increasing the temperature, and this area is proportional to the fourth power of fourth power of the temperature. Okay, this area is proportional to the fourth power of temperature, that we will discuss later. Okay, so this is the spectral distribution of black body, or energy distribution of black body. But this is the graph, and we came across some inferences or conclusions or spectral distribution of energy. But the problem is we need to explain the spectral distribution. Okay, for example, if you have a straight line, you can explain this, or we can represent this straight line with a simple equation called y is equal to mx plus c, which means that y means is a function, mx means m is the slope and x is the variable and c is the y-intercept. Okay, so the straight line can be explained with, for example, straight line can be explained with this equation. Similarly, a sine wave. Okay, the sine wave can be represented by a simple sine function sin x. Okay, similarly, this spectral line or spectral distribution of energy could be explained with a law or with a theory. So in this situation, Wiens, he proposes his Wiens law. According to Wiens law, the wavelength at maximum of spectral distribution, that is lambda max, is inversely proportional to temperature. He concluded that lambda max, I think you notice this lambda max. This lambda max is inversely proportional to temperature. As I think we already concluded that lambda max shifted towards the lower wavelength side as the temperature increases. So Wiens proposes that lambda max into T, or lambda max, is inversely proportional to temperature. And Wien also showed that energy max, or E max, is directly proportional to fifth power of absolute temperature. You don't be confused that the total energy is proportional to fourth power of absolute temperature. Just before I mentioned, see here, this area, the area means the total energy is proportional to fourth power of temperature, but here Wiens, he proposed that E max means, what is E max? The energy corresponds to the maximum wave, or this point, energy corresponds to the lambda max, so this E max is directly proportional to fifth power of absolute temperature, and he derived a formula for energy density. Expression for the energy density as per Wiens law is, look at this equation, U of nu d nu. I will explain each time. U of nu d nu, which is equal to 8 pi h nu cubed by c cubed into e raised to minus h nu by k into t. Okay, U of nu d nu, which is equal to 8 pi h nu cubed by c cubed into e raised to minus h nu by kt into d nu, where this u represents the energy and suffix nu means the frequency. So this energy density is expressed as a function of frequency. That's why we write capital U of nu. Nu means frequency, and its variable is frequency, so d nu. U of nu d nu, that is the energy density, which is equal to 8 pi. H is Planck's constant, nu is the frequency, c is the velocity of light, exponential minus h nu by k. K means Boltzmann's constant, T is the temperature d nu. Okay, this is expression as per the Wien's law. And there is what happens to this Wien's law is Wien's law could explain the higher frequency region. See, Wien's law here, this is low wavelength. Lower wavelength means higher frequency. Wien's law could explain the higher frequency region, which means that Wien's law can explain this region, higher frequency region. This region, this spectra can be explained with this Wien's law, but Wien's law could not explain the lower frequency side or higher wavelength side. Okay, Wien's law could explain the higher frequency side. Wien's law could not explain the lower frequency side. Okay, so there is a problem. A single theory or single formula could not explain the entire spectra. For example, see, there is a straight line. You explain in terms of y is equal to mx plus c. Okay, so this is valid for a certain region. The other region is not valid, which means that this straight line could not be, that is not a straight line. That graph could not be explained with this so-called y is equal to mx plus c. Okay, suppose if you have an irregular graph like triangular, for example, triangular wave. Okay, so triangular wave could not be explained with y is equal to mx plus c. Am I right? For up to I mean from one point to the another, it's okay. After that, it does not work. Okay, so Wien's law could not explain the entire frequency range. So there is a problem. Okay, so in this situation, another theory called Rayleigh and Jeans law. Rayleigh and Jeans law, they treated the radiation inside the black body as a series of standing waves. See, Rayleigh and Jeans, they treated the radiations inside the black body as a series of standing electromagnetic waves and estimated the energy density U of nu. So expression for the energy density as per Rayleigh-Jeans law is U of nu d nu is equal to 8 pi nu square k T by c cubed into d nu. U of nu d nu is equal to 8 pi nu square k T by c cubed into d nu. Okay, all terms are familiar. U is the energy. It is represented in terms of frequency U of nu d nu. 8 pi nu square, again frequency, k is the Boltzmann's constant, T is the temperature, c cubed, c is the velocity of light, and d nu. Okay, so Rayleigh and Jeans, they treated the radiation inside the black body as a series of standing electromagnetic waves and estimated the energy density U of nu. But the problem with this Rayleigh-Jeans law is it could explain the lower frequency side of the black body spectrum, but it could not explain the higher frequency side. Okay, so see, this is the black body spectra. This region is explained with the Wien's law. This region is explained with this Rayleigh-Jeans law. So Wien's law is applicable only for higher frequency side. Rayleigh-Jeans law is applicable only for lower frequency side. So there is a problem. A single theory or single formula, or we can say classical theory, failed to coin a single formula. There is a problem. Actually there is a real problem. Classical theory failed to coin a single formula for explaining the black body spectra. So in this circumstance, Max Planck, he proposes his quantum theory or quantum hypothesis, actually that removed the black body radiation from the framework of classical theory. Planck's hypothesis, which removed the black body radiation from the framework of classical physics or classical theory, and he proposes his Planck hypothesis. Okay, so in this theory, he argued that oscillating particles are responsible for absorption or emission of radiation from the black body. See, oscillating particles, as I told you, every material consists of formed by or the constituent is an atom. There are a lot of atoms in all materials. So these atoms may vibrate or oscillate. So these oscillating particles are responsible for, listen, oscillating particles are responsible for absorption or emission of radiation from the black body, which means that absorption of radiation from the black body or emission of radiation from the black body, that is due to the, or that is the main reason is the oscillating particles within the black body. So as all we know, black body contains several such harmonic oscillator. What do you mean by harmonic oscillator? Just like a to and fro motion. Okay, so black body consists of several harmonic oscillator capable of vibrating at all possible frequencies. Listen, it's very important. Black body consists of several harmonic oscillator, that is one point, and it can oscillate its own characteristic frequency, or we can say it can oscillate or vibrate at all possible frequencies. All possible frequencies. We cannot restrict this range or this one frequency. No, we cannot restrict. Black body consists of several harmonic oscillator capable of vibrating at all possible frequencies. The essential ingredient in the derivation of Planck's law is the hypothesis: emission and absorption of radiation by matter take place in discrete unit called quanta. See, discrete unit called quanta, either h nu absorption or h nu emission. H nu absorption or h nu emission. It is not continuous. It's a discrete unit of energy called quanta, that is h nu. Okay. So Max Planck, he proposes his Planck's hypothesis. In Planck hypothesis that we will discuss later, the exact hypothesis in simple words, he argued that, or he proposes that oscillating particles are responsible for the absorption or emission of radiation from the black body, and black body contains several such harmonic oscillator capable of vibrating all possible frequencies. That is important. Please note that this harmonic oscillator can oscillate all possible frequencies. And the essential ingredient in the derivation of Planck's law is absorption or emission of radiation by matter take place in discrete units or quanta of energy called h nu. Okay, I think now we can derive the Planck's radiation formula from his Planck hypothesis. Okay, I hope now you can take a paper and we can derive together. Okay, see, consider a black body which consists of n number of oscillators. Suppose there are n number of oscillators and the total energy radiated from the black body is capital E. Suppose. Then the average energy is nothing other than the total energy divided by total number of oscillator. Okay, so there is an n number of oscillator and E is total energy radiated from the black body. Okay, then the average energy is equal to total energy divided by total number. Okay, so see this E bar, that is average energy, that is equal to E by N. See, there are n number of oscillators. Then we can further classify or categorize this n number of oscillators. For example, n0 number of oscillators having energy 0. Suppose n1 number of oscillators having energy epsilon. Suppose n2 number of oscillators having energy 2 epsilon. n3 number of oscillators having energy 3 epsilon. Just like n number of oscillator or infinite number of oscillator, we can say nr number of oscillators having energy r epsilon. For example, if we conduct an examination, a few students, out of 50 students, 2 students or 1 student may have mark of 1. Then 10 students, 10 students can have mark of 20. Further 20 students, they scored 30. Okay, 2 students, they scored 50. Just like. So n0 number of oscillators having energy 0, n1 number of oscillators having energy epsilon, n2 number of oscillators having energy 2 epsilon, n3 number of oscillators having energy 3 epsilon, and nr number of oscillators having energy r epsilon. So we can write the total number of oscillators, that is denoted by capital N, that is n0 having energy 0, n1 having energy epsilon, n2 having energy 2 epsilon, etc. So total number of oscillators is n0 plus n1 plus n2 plus n3 plus etc. up to nr. That is the total number. Okay. Then the total energy is n0 into 0. For example, if you want to calculate the total mark of all the students in a class, which means that 2 students into 1 mark plus 10 students into 20 mark plus 20 students into 40 mark plus, so we will get the total mark of a class. Just like the total energy radiated from this black body is, we can calculate like 0, which means that n0 into 0 means 0 itself. So we can write n0 into 0, that is 0, plus n1 into epsilon, that is epsilon n1, n2 into 2 epsilon, that is 2 epsilon into n2, n3 into 3 epsilon, that is 3 epsilon into n3, etc. up to r epsilon into nr. I think up to this it is very clear. N is the total number of oscillators, E is the total energy. But the problem is, depending upon the situation or temperature, the number of oscillators possessing particular energy may vary. For example, just before I mentioned an example of marks scored by students in a particular class. Suppose if you study well, you will get more mark. Okay, so your mark, just before I mentioned that 2 students, they are scoring mark 1. It is not constant, which means that all the exams they are scoring mark 1. No, it is not this situation. It is always changing depending upon the condition. Similarly, depending upon the condition, the number of oscillators having a particular energy, for example, n0 number of oscillators having energy 0, that may vary or that may change. So that change is a function of temperature. So using Maxwell's statistical distribution law, n1 is the number of oscillators having energy epsilon. We can write this as a function of n1 is equal to n0 exponential minus epsilon by kt. Similarly, n2 is equal to n0 e raised to or exponential minus 2 epsilon by kt. Or we can say nr is equal to n0 e raised to minus r epsilon by kt. This is as per Maxwell's statistical distribution law. N is the total number of oscillators having energy E. So the average energy is equal to capital E by N. Total number of oscillators, we can say N0 plus N1 plus N2 plus etc. up to Nr. Then total energy is equal to 0 plus epsilon N1 plus 2 epsilon N2 plus etc. up to R epsilon Nr plus etc. Okay. Now, using Maxwell's statistical distribution, I think it is clear that how it came. Depending upon the temperature or condition, the number of oscillators possessing a particular energy, that may vary. So that may vary means, for example, suppose the temperature is 1000 Kelvin, there is N1. If it is 2000, the value of N1 may change. Okay, so it is a distribution, it obeys distribution law. So this is as per the Maxwell statistical distribution, we will get like this. Okay, so see, n is equal to n0 plus n1 plus n2 plus etc. up to nr. Okay, so we can write n is equal to n0, see, n0 plus n1. Instead of n1, we can write n0 e raised to minus epsilon by kt plus again n2 n0 e raised to minus 2 epsilon by kt plus etc. up to nr, again n0 e raised to minus r epsilon by kt. Look at that equation. I hope you can derive this equation along with this presentation. See, n is equal to n0 plus n0 e raised to minus epsilon by kt plus etc. Okay, so in this equation, what is common is n0 is common, so we can take this one outside. So n0 into 1 plus e raised to minus epsilon by kt plus e raised to minus 2 epsilon by kt plus etc. up to e raised to minus r epsilon by kt. So inside the square bracket, it is just like a binomial expansion. I hope in your pre-degree or sorry plus 2 levels or plus 2 class, you may heard about binomial expansion, or in your degree class itself, binomial expansion. 1 plus x or 1 minus x all raised to minus 1, that is equal to 1 minus x all raised to minus 1, which is equal to 1 plus x raised to minus 1 plus, or x 1 plus x square plus s cubed plus etc. Just like. So this, as per the binomial expansion, this term inside the square bracket can be written as, please write, n is equal to n0 into the square bracket can be written as 1 minus e raised to minus epsilon by kt all raised to minus 1. Please write n is equal to n0 into the inside this one is as per the binomial expansion, we can write n0 into 1 minus e raised to minus epsilon by kt the all raised to minus 1. Something raised to minus 1 which is in the numerator, we can take that to the denominator. So what happens is n is equal to n0 divided by 1 minus e raised to minus epsilon by kt. So this is one equation. Please keep it for further calculation. N is equal, once again I would like to tell you, n is equal to n0 plus n1. This is n2, then n3, etc. up to nr. Okay, from this n0 is common, so we can take this one outside, and inside the bracket is 1 plus e raised to minus epsilon by kt plus e raised to minus 2 epsilon by kt plus etc. up to e raised to minus r epsilon by kt. Inside the bracket there is a binomial expansion, so we can write n0 into 1 minus e raised to minus epsilon by kt all raised to minus 1. All raised to minus 1 is in the numerator, so we can take this one to the denominator. So we will get like this. That is the total number of oscillators in a black body. Next one is the total energy radiated from this black body. So total energy is equal to n0 into 0, that is 0, plus epsilon into n1, first energy. Then 2 epsilon into n2, the second, etc. up to r epsilon into nr. So we can write 0, that is 0 is there. Epsilon into n1, instead of n1, what we can write is n0 e raised to minus epsilon by kt. Okay. Similarly, 2 epsilon into n2, n0 into e raised to minus 2 epsilon by kt plus etc. up to r epsilon into n0 e raised to minus r epsilon by kt. So what is common in this term? That is epsilon n0 e raised to minus epsilon by kt. This term itself is common in all other terms. So we can take this one outside. This first term is 0, that we can remove or neglect. Remove that one. So this term is taken outside. So in this place there is 1. Epsilon n0 e raised to minus epsilon by kt, that is taken outside. So 1 plus 2 epsilon n0 e raised to minus epsilon by kt is taken outside. So 2 is there. Epsilon n0, that is always taken. That is taken. The remaining term is 2 e raised to minus epsilon by kt. 1 minus epsilon by kt is taken outside. So remaining term is 1 plus 2 e raised to minus epsilon by kt plus etc. up to we can write plus etc. 3 e raised to minus 2 epsilon by kt, or r e raised to minus of r minus 1 epsilon by kt. Please note 1 plus 2 e raised to minus epsilon by kt plus 3 e raised to minus 2 epsilon by kt. The last term is r e raised to minus of r minus 1. See, look at this one, r minus 1. Okay. I think it is clear. Now look at this square bracket. This is again a binomial expansion. So as per the binomial expansion, see epsilon n0 e raised to minus epsilon by kt, that is first time, into 1 minus, you can write 1 minus e raised to minus epsilon by kt, the all raised to minus 2. This is as per the binomial expansion. 1 plus 2x raised to minus 1 plus 2x plus 3x square plus etc. So this is as per the binomial expansion. So we can write epsilon n0 e raised to minus epsilon by kt into 1 minus e raised to minus epsilon by kt all raised to minus 2. So all raised to minus 2 that time is in the numerator. So we can take that one in the denominator. So we will get the total energy is equal to epsilon n0 e raised to minus epsilon by kt divided by 1 minus e raised to minus epsilon by kt, the all square. So minus 2 in the numerator, that comes to the denominator. So it is plus 2. So the total number of oscillator is this, and total energy is, what is average energy? Total energy divided by the total number. So average energy of the oscillator is E bar is equal to total energy divided by total number. So this is the total energy, epsilon n0 e raised to minus epsilon by kt divided by 1 minus e raised to minus epsilon by kt, the whole square, divided by the total number. Okay, n0 divided by 1 minus e raised to minus epsilon by kt. So from this expression you can find this n0, see this n0, I think you can see the cursor, this n0 and this n0 get cancelled. Okay, then 1 minus epsilon by kt one time is here, 1 minus epsilon by kt the whole square. So one term or one power may get cancelled. So remaining energy is, or remaining factor is, E bar or average energy is equal to epsilon e raised to minus epsilon by kt divided by 1 minus e raised to minus epsilon by kt. Is it clear? E bar or average energy, which is equal to E bar divided by N, which is equal to E, we write here, N, that is here. So in this expression, see this n0 and this n0 get cancelled, and one term, this term and this term get cancelled. So remaining is this one. And if we multiply numerator and denominator with a particular value, it won't affect. Okay, so we multiply the numerator and denominator with the same value. That value is e raised to epsilon by kt, not e raised to minus epsilon by kt. It is multiplied with e raised to epsilon by kt. So what happens here? Epsilon into e raised to minus epsilon by kt into e raised to plus epsilon by kt. What happens? E raised to m into e raised to n. That is e raised to m plus n. Here e raised to minus epsilon by kt plus epsilon by kt, so it will cancel. So e raised to 0 is 1. So the numerator is epsilon itself, that is epsilon. In denominator, if you multiply 1 with e raised to epsilon by kt, that is e raised to epsilon by kt itself. And here what happens? E raised to minus epsilon by kt into e raised to plus epsilon by kt, that is 1. So the average energy E bar is equal to epsilon by e raised to epsilon by kt minus 1. Okay, so again I would like to tell you the average energy E bar radiated from the black body is epsilon by e raised to epsilon by kt minus 1. And according to quantum theory, we know the energy radiated or absorbed in the packet of energy called quanta, that is h nu. So epsilon is equal to h nu. So instead of epsilon we can write h nu. So E bar is equal to h nu by e raised to h nu by kt. That is the average energy radiated from the black body. So the average energy radiated from the black body is E bar is equal to h nu by e raised to h nu by kt minus 1. Now we have to find the energy density, or number of oscillators per or unit volume. So the number of oscillators per unit volume in the frequency range nu and nu plus d nu is given by or the density of standing waves in a cavity is given by n is equal to 8 pi nu square d nu divided by c cube. See, the number of oscillators per unit volume. The number of oscillators per unit volume is, see, for example, density means density is mass divided by volume. That's density. Okay, so number of oscillators per unit volume means the number by volume. So number of oscillators per unit volume, what we get is number density or density of standing waves in a cavity. Density of standing waves in the cavity. The standard formula, that is n is equal to 8 pi nu square d nu divided by c cube. It's a standard one. The number density. And if we multiply this number density, n is equal to 8 pi nu square d nu divided by c cube into the average energy. So if we multiply this number density with average energy, what we will get is energy density. So number density n is equal to 8 pi nu square d nu divided by c cube times the average energy. Average energy is E bar is equal to h nu divided by e raised to h nu by kT minus 1. So the number density multiplied by average energy of an oscillator gives the energy density of the radiation in the range nu plus d nu. See, black body consists of radiations of all wavelengths. All wavelengths. See, this spectrum like this. Okay, so if we take a small frequency range nu and nu plus d nu, the energy density corresponds to that frequency range is denoted by this formula u of nu d nu. I hope it is clear. Okay, E bar is the average energy, n is the density of standing waves. The energy density from a black body for a frequency range nu and nu plus d nu, which means that very few frequency range, a small range. It is denoted by this formula u of nu d nu 8 pi nu square d nu by c cube, that is the number density times h nu by e raised to h nu by kT minus 1. Okay, for example, for a straight line, a small, suppose there is a straight line, a small area can be represented by y is equal to mx plus c. Okay, it is represented by this area and the full range also. Okay, so this Planck's radiation formula, it is represented by small frequency range. It is applicable to full frequency range also. We will check whether it is applicable or not. For example, see the Wien's law, which could not be explained, or the Wien's law can explain the higher frequency side, you could not explain the lower frequency side. But we will check whether this Planck's radiation formula valid for the entire frequency range. Okay, so the energy density u of nu d nu is equal to 8 pi nu square d nu by c cube into, this is number density and this is the energy, average energy, not energy, average energy. That is the energy density u of nu. This u means energy density and suffix nu means it is expressed in terms of frequency, not wavelength. Okay, so this is the well-known Planck's radiation formula. So this is the Planck's radiation formula, that is u of nu d nu, that is equal to, it's combined 8 pi h nu cube divided by c cube into d nu by e raised to h nu by kT minus 1. This is the so-called Planck's radiation formula. And this Planck's radiation formula and this Planck's radiation law agrees well with the experimental curve over whole range of frequency in the black body spectrum. So the black body spectrum as graph is like this. Wien's law can explain the higher frequency side. Rayleigh-Jeans law can explain only the lower frequency side. But the Planck's radiation formula, which can explain the entire frequency range. Okay, so the problem with the black body radiation is rectified with this Planck's radiation formula. Okay, this Planck's radiation formula can also be expressed in terms of wavelength. You just note down this one. It can be explained in terms of wavelength. For example, this frequency can be expressed as in terms of wavelength as nu is equal to c by lambda and d nu is equal to c by lambda square and d lambda. You just take the derivative with respect to lambda. Okay, so it can be expressed in terms of wavelength also. Okay, It's clear? Just write the expression for Planck's radiation formula in terms of wavelength. That's all. Here, the standard Planck's radiation formula in terms of frequency. Okay, you should derive this Planck's radiation formula. Then see, this is the Planck's radiation formula for a particular frequency range nu and nu plus d nu. See, this Planck's radiation formula u of nu d nu, which means that this radiation formula for a particular frequency range. If you want to know the total energy radiated from this black body, what we should do? We should integrate this frequency from lower frequency side to the higher frequency side, which means that in general we can say we can integrate this equation from frequency minus infinity to plus infinity. I think you remember that just before I mentioned that the oscillators can oscillate all possible frequencies. Okay, black body consists of n number of harmonic oscillators, and each oscillator can oscillate its own characteristic frequency, all possible frequency. So the total energy radiated from the black body can be calculated using this radiation formula by integrating the frequency from minus infinity to plus infinity. So the total energy density of black body can be calculated using, sorry, not minus infinity, 0 to infinity, sorry, 0 to infinity, from 0 frequency to infinity frequency, not minus infinity. Okay, the total energy radiated from this black body can be calculated from frequency 0 to frequency infinity, maximum frequency. So after integration, what we get is total energy radiated from the black body is equal to 8 pi raised to 5 k raised to 4 t raised to 4 15 h cubed c cubed. After integration, see, after integration and substitution for frequency 0, frequency infinity. So what we get is this equation. Here 8 is a constant, pi is also constant, Boltzmann's constant itself is a constant, 15 is a constant, h is Planck's constant, that is also a constant, c is the velocity of light, that is also constant. So see, these values are constant. That means other than temperature T, all these values are constant. If we substitute the value, what we get is a constant. That constant is denoted as sigma. So we can write U is equal to sigma T raised to 4. This sigma is a constant, or we can say the total energy radiated from this black body is proportional to 4th power of temperature. See, while explaining the Rayleigh-Jeans law, I mentioned that Emax is, sorry, Wien's law, I mentioned that Emax is proportional to 5th power of absolute temperature. But here the total energy, not Emax, the total energy radiated from the black body is proportional to 4th power of absolute temperature. And sigma is a constant. That constant is called Stefan's constant. That sigma is called Stefan's constant, and this is Stefan's Boltzmann's law. So the total energy radiated from the black body is equal to sigma T raised to 4, that is Stefan's law. Okay, so this is the total energy radiated from the black body, and this Planck's radiation formula, see, this is the Planck's radiation formula which agrees the all frequency spectra. So the crisis related to this black body is solved. Now we would like to check whether this Planck's radiation formula reduces to Rayleigh-Jeans law or reduces to Wien's law for respective frequencies. For example, for low frequency, this Planck's radiation formula should reduces to Rayleigh-Jeans law. At low frequency, the Planck's radiation formula should reduces to Rayleigh-Jeans law. Planck's radiation formula should reduces to Rayleigh-Jeans law, because at low frequency the Rayleigh-Jeans law is good enough. The entire black body spectra, consider the entire black body spectra. The lower frequency side can be explained with the Rayleigh-Jeans law. So we will check whether this Planck's radiation formula reduces to Rayleigh-Jeans law, whether the Planck's radiation formula reduces to Rayleigh-Jeans law at a lower frequency limit. So lower frequency means frequency is very small. So we can write h nu by kt is again very much less than 1. Okay, so it is very much less than 1. So we can write, suppose e raised to x, the expression for binomial expression for e raised to x, for example x is very much less than 1, we can write 1 plus x square by 2 factorial plus etc. E raised to x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus etc. like that. Then higher order term, since x is very small, higher order term can be neglected. Similarly, e raised to h nu by kt, here the h nu by kt is very much less than 1, so we can write 1 plus h nu by kt plus h nu by kt the whole square etc. That whole square or higher order term can be neglected because h nu by kt is always less than 1. For example, suppose h nu by kt is 10 raised to minus 3. For example, h nu by kt is 10 raised to minus 3, then h nu by kt the whole square is 10 raised to minus 6, which is very much less than 1. So we take the first two times also. So 1 plus h nu by kt. So instead of this h nu by kt, if you substitute the value of 1 plus h nu by kt, what happens? This 1 and this 1 will get cancelled. So what we get is h nu by kt itself. Okay, I think you can write itself. Write it in a paper. Instead of this e raised to h nu by kt, you can write 1 plus h nu by kt. Okay, then that 1 and this minus 1, this positive 1 and this negative 1, that will get cancelled. There is h nu by kt, that kt goes to the numerator. There is h nu, here there is an h, that will get cancelled. Then here is nu cubed, here is nu, so there is nu square. So what we get is 8 pi nu square c cubed, then there is a kt. So what we get is 8 pi nu square kt divided by c cubed into d nu. This is nothing other than Rayleigh-Jeans law. So at a low frequency limit, this Planck's radiation formula reduces to Rayleigh-Jeans law. Now at the higher frequencies limit, so we will check. This is Planck's radiation formula. At a higher frequency limit, h nu by kt, which is very much greater than 1. See, h nu by kt is very much greater than 1. So if h nu by kt is very much greater than 1, so e raised to h nu by kt minus 1. Since h nu by kt is very much greater than 1, e raised to h nu by kt, which means it's a very big value. That very big value minus 1. For example, 1 crore minus 1. That 1 can be easily neglected. So e raised to h nu by kt itself. So e raised to h nu by kt minus 1, this minus 1 is neglected because the e raised to h nu by kt is a very big value. So here e raised to h nu by kt itself. Since it is a denominator, so we can take this one to the numerator. So what happens is e raised to minus h nu by kt instead of h nu by e raised to h nu by kt. So what happens is 8 pi h nu cubed divided by c cubed into e raised to minus h nu by kt into d nu. So this is expression. This expression is nothing other than Wien's law. Okay, so the validity of this Planck's radiation formula means the classical validity of Planck's radiation formula, or the validity of this classical theory, Wien's law. Classical theory in the sense Wien's law. Validity of classical theory means the validity of Wien's law and validity of Rayleigh-Jeans law. That is we check it. Okay, so at a higher frequency limit, this Planck's radiation formula reduces to Wien's law. At a low frequency limit, Planck's radiation formula reduces to Rayleigh-Jeans law. Okay, so at a higher frequency limit, it reduces to Wien's law. At low frequency limit, it reduces to Rayleigh-Jeans law. Okay, so one problem is solved. So this is about the Planck's radiation formula, the derivation of Planck's radiation formula, or that's about the explanation of spectral distribution of black body. Okay, so next class we will discuss something about another theory called photoelectric effect. Okay, thank you.